with. We have, let's see, we were doing empty model. You successfully interpreted the interclass correlation. So yes, 39% of the variation is because some girls behave more badly on average. Risky behavior is the outcome we're predicting. The fixed effects in this model, there's only one, it's right here. So 19 is the average score over time. So the purpose of this model is to provide a baseline for comparison as we add terms to see if they help the model fit better and explain variance. So this is a useful descriptive statistic, but we know that it's probably not going to be sufficient based on our earlier inspections of the data. It is possible to test whether or not this random slope variance of 10 is necessary. So in other words, is this intraclass correlation of 0.39 significantly greater than 0? We can do a likelihood ratio test to answer that question. So within Elmer, I found a function called RANOVA. That's what I call it. R ANOVA, I think, is where they were going with that. But I like to make the joke that in teaching these models, I feel like I've been run over. Ba-doom. We call that a rim shot. So ANOVA-like table, it is doing the likelihood ratio test before you. So here is the log likelihood of the model that does not have a random intercept in it. Here's the log likelihood of the model that does. -2 times the difference in these numbers is your test statistic. This is supposed to be distributed approximately as a chi-square, where the critical value to add one term would be 3.84 under a standard 1 degree of freedom distribution. It's 300 and something, so yeah, that's more than 3. So yes, we absolutely need the random intercept in the model. This intraclass correlation is significant. So one thing that I was not able to get out of Elmer without doing the matrix algebra myself, which I did not want to do, is the total marginal predicted matrix. So I have pasted an output from what is given in the SAS program, their mixed routine. This is what the model is predicting the variances and covariances over time should look like. According to the empty model with only a random intercept, each of these variances at each occasion is partly due to the random intercept, and the rest of it added together is the residual. So this 10.8 plus 17, that's where this 28 comes from. So this is what the model says the data should look like. We already know that this isn't going to fit because I have the answer key approximately right here. This is what the data say. So we'll keep it moving. So adding fixed linear exact age. So not rounded into convenient intervals of 12, 13, 14, but using exact age. And so I've written the equation to show the centering directly. That way anyone looking at your equation will know how you set up your variables. So we're calling age minus 18 time. That's the variable in the syntax. So here's my next model, model 2A as I've called it. I've abbreviated it as an object fixed linear. And the addition to the formula is right here. There's time as a new fixed effect, a linear effect specifically. Everything else is the same. So because we are using regular flavor maximum likelihood, I could do a likelihood ratio test against the previous model if I wanted to. However, for fixed effects, you can always just check the p-values. So here's my new term. That's my new fixed slope. The inclusion of that term has resulted in changes to my variance components. So here's where it gets interesting. Let's start with the variances first. Or let's start with a question first, even better.
I'm confused.
Yeah.
I thought we used age as a predictor, but now it says time. What do you say aging is time, basically?
Yes, I am. So time is the name of the predictor that I created back at the beginning, right here. So it's age minus 18 is a new variable that I'm calling time. So you could call it age, but I wanted to differentiate the centered version from the uncentered version. And age 18 was what it was called in the wide data set, which is yet a third possibility. So to make sure that none of the names overlapped, I changed it. So it's purely a semantic distinction. So time is age minus 18. Thank you for the question. In this case, that's all we need because everybody was approximately 12 when the study started. If we had sampled people from different ages over time, then we would need both cross-sectional age at entry as well as time in study as two separate terms. That's chapter 10, though, not this one. Okay, other questions? All right, moving along then. Back to page, let's see, this is page 5. That's where we are. Okay, so relative to the previous model, our variances changed. One went up and one went down. The one that went down is the level 1 residual variance. Relative to the previous model, it decreased 34%. That is as it should be, because what we had previously were just means with no slope, and we've added a slope. So what used to be residual error around the line should be less if we draw a better line. So we drew a sloped line instead of a flat line, and that explained 34% of what we were calling within-person variation actually had to do with which occasion was which. Because the random intercept variance went down, because the residual variance at level 1 went down, that caused the level 2 random intercept variance to go up 7.5%. So this was what I was talking about earlier. I have a slide on it somewhere in here. It's under details. This one. It's described on slide 86. But what happens is there is less of a correction factor subtracted off of the estimate that forms the random intercept variance than before, and that makes the random intercept variance go up. So the intra-class correlation changes after you add predictors, in part because the predictors explain things, but also because of this yoking together of the two. So big picture, this is not a problem. It is an expected consequence of explaining level 1 variance. In some textbooks, you will read that if your variance goes up, that's an index of model specification. Not in this case. It is not. It is a consequence. So the way that I would talk about it is just to say that the effect of linear age is time, explained 34% of what was within-person variance at level 1. The end. And that reduction is statistically significant according to the results for the fixed effects here. So we have now an intercept that reflects the expected risky behavior at age 18 specifically, conditional on when time 0 is, and then time describes the increase in risky behavior per year up to that point. So for every year older the girls get, on average, they increase in risky behavior by 1.12. And here's my p-value that is significant to 16 decimal places. Okay, how are we doing? Thumbs, excellent. So if you want it to do the math for you, there are many ways to generate model predicted outcomes. The code that I have written here is designed to be the most transparent, not the most efficient. Two different things. So I am using a routine within the, Elmer test package, I think, called Contest 1D, which is the idea of asking it to do math on your fixed effect coefficients. So do you see the two numbers in here? In each of these statements? They are multipliers of their corresponding fixed effects in order of entry into the model. So what I'm asking for here is the predicted intercept at age 12, which is a function of starting at 22, so that's what the 1 does, plus minus 6 times my slope fixed effect. because it's -6 is when we're at age 12 relative to time centering. So it's -6, -5, -4 as we go from 12 to 13 to 14, ending at 18 as the 0. So the result of these lines is given below. These are the model predicted means at each age. So that's how you could use these numbers to draw a function of what the model predicts in terms of the linear slope for change. Does that make sense? Have you seen these sorts of statements before? See, I didn't learn about these until I was on the tenure track, and I really wished I would have seen them before. But you can make it do math on your fixed effects to get any kind of predicted value or any other kind of linear combination of your fixed effects. This is just one instance of it. So again, these are multipliers of the fixed effect estimates. So this means take 1 times 22 plus -6, which is the value of time at that occasion, times the slope. And then it spits out the answer from that linear combination. And the answer is this 16 right here. Not better? Those are sideways looks if I ever saw one. Maybe if we do another one, it might work better if you can see more instances of how one would use this, maybe. And maybe it's just because it's like 4:45 in the afternoon. They're confounded, right? You can't draw any conclusions. So I've got them all here. This is what the model predicts. So far, the model says everybody changes the same. That is unlikely to be true. Let's see if they need their own. So I am adding this U1 term, here's my equation right here, that allows each girl to have a different linear slope rather than sharing the fixed slope. What the model is eventually going to predict in terms of the marginal variance covariance matrix that these three variance components and their covariance here imply is given right here. So this is from chapter 6 in my book as well. It predicts that the variances change over time in this function. It's a function of time squared, and the covariances change over time as well. And this is the marginal variance covariance matrix printed out of SAS, again, because I couldn't get Elmer to give it to me easily. And this is what it looks like. So it's predicting that the variance is decreasing and then increasing. So it's that sort of parabola of changing variance over time is what the model's predicting. And the covariances do a similar idea, but with this function right here. How do I know if we need this new U1? That's a likelihood ratio test. So in Elmer, let me try to squish these together. There we go. It doesn't give you any standard errors or p-values or anything for your variances. That is as it should be, in that we can't use those standard errors to form a wald test because variances aren't normally distributed. And the closer they get to 0, the more that is true. So rather than asking whether this number is different than 0, what we will do is compare it to the previous model that didn't have it in there and see if it helped. So it gives you the level 2 intercept variance, which is now specific to age 18. It gives you the linear slope variance, and it gives you the correlation between the intercept and the slope. So Viola, I'm going to call on you for this one since you asked the question. What does this number mean? 0.7 is the correlation between the intercept and the slope. How do I interpret that properly?
So you centered the time to 18, so
Yes.
that means that where girls end up in age 18 is positively correlated to the slope, meaning that high negative behavior at age 18 also means that there was a higher increase in this behavior over time.
Yay, perfect. Good work. Yes, but at age 18 is the critical part of the sentence, because this number would change if it were time 0 at someplace else. So it gives you the correlation. You could convert it into the covariance if you wanted to. here are the two fixed effects. The only difference is in the standard errors. So the standard error for this time slope is going to be larger once the random slope is in the model. That means that in order to have it be correct, we need to have the random slope in if it's needed. And the same code, other than referring to my new model, is here because the fixed effects haven't changed. These are describing the average trajectory, which is exactly the same as what it was. And we get down to, here's my RANOVA for random linear. And so here is the comparison model, and here is the model without random time in it. And it looks like my test statistic is 120 on degrees of freedom 2. Why do you think it's 2 instead of 1? Any guesses? What are the two parameters that I added to this random linear model to differentiate it from the fixed linear model? I'll give you one of them. The random slope variance. The covariance. Ding, ding, ding. Yep. Whenever you add a new random effect, you have to add all the covariances of it with the random effects that are already there. Because the U's from the same person are going to be related. So it's 2 degrees of freedom, and the test result says, yep, it helps the model to keep it. Now at this point, I would not do any pseudo R-squares for the addition of the random slope because it doesn't explain variance. This is a point where my opinion differs from other people, but I'll give you my opinion. What we have done is partition variance. We have taken what used to be residual and split out how much of it is because people change differently. But to me, I would never say that we have explained it, because we don't know why people change differently. We know that they change differently. So it's still error, it's just a more specific kind of error. What we know is that people start out different, or people end up differently at age 18. People change differently to get there. We don't know why. And then there's still error around the growth curves as well. So 3 different kinds of error, to me, does not mean explain variance. But people would disagree with that. So, because the trajectory looked bendy, I'm going to add the fixed quadratic term. So in the equation here, note that it's just the new gamma term here for beta 2 and no u that goes with it. And this is the new piece in the equation, I times squared, which is how I figured out how to do squared things. It wouldn't let me do the variable colon variable when it was the same variable. If this doesn't work, you can make a squared variable manually and stick it in. I've done that before too. Because it's a fixed effect, we can stare at the p-value that goes with it. Survey says, yes, significant at a conventional alpha level of 0.05 or even 0.01, so that means that we need to keep it. Its inclusion further reduced the residual variance by another 4% relative to the previous model. So part of the reason why people were off their line is because the line needed to be bendy and not straight. But it's still the same amount of bendy for everybody. Bendy is the technical term that goes with acceleration here. So same bendy, different linear slopes is what this model says. So if I were to interpret the fixed effects then, 23 is what? My fixed intercept is 23 and some change. Yep, that's the model predicted average risky behavior at 18. So it's based on where the trajectory is, not exactly at age 18, but where the line ends. Yep. And this slope is about 2. What's that? It per year, but at age 18 also. Because of the quadratic, it's also conditional. So it's the slope at 18 specifically. This way, right? That better? Okay. And then this term. What do I do to it to interpret it? I got to multiply it by something. 2. Yes, indeed. So twice the quadratic, so like 0.29, we'll say, is how the linear slope changes per year. So this is a pattern of accelerating this way. Accelerating increases. The linear slope becomes more positive as time goes on, ending up at a slope of 2 by the time they're 18. So I can figure out what the model then would predict at any age. Here's our friends, the linear combinations. So let's start with the last one. This is how I would generate a predicted value at age 18, because that's when time is 0 and time squared is 0. Age 17 would be -1 for time, squared is 1. Age 16, -2 squared. So these are the multipliers that are the variables that the slopes are multiplying. Nothing is multiplying the intercept, that's why it's a 1. So then here are the predicted values at age 12, age 13, age 14 that we could use to make a trajectory and a picture ourselves. Now here's a different version of a prediction, the slope at each occasion. The slope that's given directly by the model for the linear slope is at 18. But I can get it for any level. And now I'm looking at this and seeing a typo. I will fix that one too. That should be a blue 0 right here, because that's when time is 0. So the trick to getting model predicted linear slopes is to multiply time by 2. So that's what the term that multiplies the quadratic is time times 2. And so then here are the model implied linear slopes at each age. So the last one should have been the one that's given by the model, and you can see that it's less positive as you move back down in age. So even though I centered it at 18, I can ask for the predicted outcome and the predicted linear slope at any age as a linear combination of my fixed effects. It's all good. And I decided to output predicted values so that I could do a total R². So I'm using the predict function without random effects in it, so predicted only from the fixed effects. I then saved that variable as pred from the unconditional model, meaning just time. I then saved the correlation between the predicted outcome and the real one and squared it, and I get this number. What that number means, 0.19, that is the total amount of variance that fixed effects of linear and quadratic age explain in risky behavior, put back together again. So it's a complement to the pseudo R² of how much you got out of each pile. Last but not least, do you think each of the girls might need their own bendy? Maybe. It's worth a try. So here is what the model predicted variance is at each occasion. It is a function of time to the 4th power. And the covariance between occasions is this messy thing too. So it's still the idea that the random slopes are allowing heterogeneous variances by time, but exactly what that heterogeneity is depends on the form of the model. Here's the marginal covariance matrix that is given by those two equations. Here is the new quadratic term. It's inside the parentheses, so that's my random quadratic addition right there. Results, here is my new variance component. I can't stare at it and make any sort of decisions. I need to do a likelihood ratio test. And note that it got mad at me. I don't know exactly what this means, but it doesn't sound good. optimizer convergence code failed to converge maximum gradient. That means that it couldn't really find the best answers. And turns out there's a reason for that, because the random quadratic on the likelihood ratio test was non-significant. So we don't really need it. And in fact, it's not in the simulated data. So that is what it should be. So here's a comparison then of the different predicted models. The saturated model is the solid black line here. The empty model with no effects of time in it is the flat one. And then we can compare the relative improvement of linear versus quadratic. And quadratic does a pretty good job because, again, that's how I simulated it. So it could be done. But reviewer 2 wants me to see if there's any residual correlation left over. So I can do that. But in order to do that, I got to switch packages because Elmer won't let me do that. So I'm switching to the LME package within NLME because that will allow me to have random effects as well as some kind of residual correlation over time. So the model is the same. This is my intercept linear time, quadratic time is fixed effects. The random component is defined like this, so the syntax is a little bit different, but it's similar enough to where you can hopefully follow it. The new part then is this thing right here. That is allowing a autoregressive relationship among the residuals, such that the ones that are correlated 1 unit in time apart are correlated R, 2 units in time are R squared, 3 units in time are R cubed, and so forth. Here is my new residual correlation parameter. It's 0.02. That's pretty tiny. And indeed, if I do a likelihood ratio test against the previous model, it doesn't really help. And so I won't end up keeping it. In order to do that, though, I had to re-estimate the other model using LME so that it was the same. Then I can use ANOVA to compare the two. So reviewer 2, thank you for that helpful suggestion. We did examine the potential for residual correlation and found it did not significantly improve the model, and therefore we did not include it. Thank you. Have a nice day. All right. One last model, folks. It's 5 o'clock. Do we have enough strength for one last model? Maybe? Okay. I think we can do it. I know I can do it. If you can't do it, it's okay, but we're going to try. So given that I don't need residual correlation, I can switch back to Elmer. I am including parent attitudes in 3 different places here as a predictor of the intercept, linear, and quadratic slopes. So the idea would be that children whose mothers have more conservative attitudes maybe have less risky behavior, if parent opinions matter. I'm not sure that they do, but we can find out. So I have added these terms right here to the model. Main effective attitudes, attitudes as a multiplier of time. So that's my attitudes by time interaction. And then attitudes by time squared interaction. So that corresponds to gamma 01, gamma 11, and gamma 21 respectively. So I have indicated how the variance components changed as a function of those 3 new fixed effects. And here are the 3 new fixed effects. So it looks like we have a significant effect of attitudes by itself. So given the rest of the model interaction terms, this is conditional on age 18. So at age 18, for every unit more conservative your mother's attitudes were measured at age 12, then your risky behavior is significantly lower by 3. So it did help, I guess. Here is my linear slope at 18. It's about 2 again. The interaction term is going to make it less positive. So girls who have more conservative mothers increase to a lesser extent at 18. They don't go down, they increase less. And then the quadratic part, there is an increase in the slope from 12 to 18, but it looks like there's not a significant effect of attitudes on that. So conventionally non-significant there. So the prediction of this model then is shown in this picture, which I made in Excel, and that Excel sheet that I made it from is in your download packet as well. So we have attitudes of 4 as the middle line as the reference, and then the rest of this shows what the model predicts. The main effect covers the distance at the end here. This should be occasion as the label. I need to fix that. And then the differences in linear slope are at the end as well, but it looks like there's not much change in the quadratic. And those three terms, respectively, the main effect explained 16% of the intercept variance, the interaction with linear time explained about 16% of the time slope variance, and the interaction with quadratic time actually explained the residual. So this one is a little bit controversial. Some people would say, you can't do that. And to them I would say, I just did. It's because there's no u here. The rule is a time-invariant predictor explains the u variance in its row. If it's not there, the only thing left for it to explain is e. So the interaction of attitudes by time squared can indeed explain e, even though attitudes by itself cannot. And the term for that, I would say, is systematically varying effects. It's a middle ground between fixed, everybody gets the same, random, everybody gets their own. We're saying you get your own systematically as a function of attitudes, but not randomly otherwise. The trick to pulling this off is to make sure that you don't need the u in there in the first place. If you do need it and you leave it out, then it's a problem. But I tested it before and I didn't simulate it in the original data, so I feel pretty good about leaving it out. And then we can get some total r square using the predict function as well. We can get the new total r square after including attitudes, and this is the change in r square. So we have about 5% of the overall variance in risky behavior that is captured by including the 3 fixed effects of mother's attitudes. So that's a supplemental piece of information beyond just the idea of pseudo r square per pile explained variance. Ta-da! And here's the same model in Lavon. So I have a couple typos in here that I need to fix, and I will repost that stuff once it's fixed, but otherwise, here's the output that we get from that. The model fits quite well, as I expect, since I made up the data. And I have labeled off to the side here the correspondence between all the parameters in the mixed effects multi-level version and the SCM version. And indeed, there's a one-to-one correspondence. The only difference, there's very few differences because this is assuming perfectly balanced time rather than exact time, because Lavon doesn't do exact time, as far as I know. All right. And if you wanted to know some of the words that I would use to describe this, it's in chapter 7 of my book. That's where this example came from. So the activity then that I had suggested one can do is to predict time-varying monitoring as an outcome instead. So rather than predicting risky behavior, predict time-varying monitoring and tell me if you end up at the same place. And if you don't want to do that right now, that's fine with me. If you do want to do that right now, I'm happy to hang out. The other piece of this, example 1b, has that last model in M+. So if you want to learn M+ code, this is how we would do a standard multi-level model in M+. And I can go over that, or I can save it for tomorrow. What do you think? Any votes? Go over it now or save it till tomorrow?
I have to go.
So your vote is to save it.
You start with 9 tomorrow, and maybe we can then.
Yep. Then I'm going to call it. We're going to go over this tomorrow. Yeah. So yes.